Okay, sorry guys. So anyway, to me the diodes, I think the main benefit they gave us was an asymmetric response. For example, if you look at this voltage versus current curve, for resistor, basically you have so basically you have just I is equal to V over R. It doesn't matter if V is negative, if V is positive, that's your equation. But for a diode, we get this nonlinear response. So, we can start getting, we can basically use it to do more things. So basically we can get these switching points in our circuits, like you guys saw in the homework, things like that. We can get regulators, rectifiers, limiters. There's a bunch of other circuits that, that we didn't talk about. So, so the next tool we're talking about is the transistor. And we're going to talk about two types of transistors in the class. Today we're going to talk about bipolars, but the two main types of transistors are, bipolar and MOS transistors. Okay, and just a note to maybe impress you guys, but I was looking at Wikipedia to come up with interesting numbers. So it said between 1960, just to give you an idea how important transistors are, I'm sure you know, and 2018. So between these years, 1960 is not quite the year the transistor was invented, but quite close. And we're still a couple of years short of what we are at. It said that estimated a total of 6 trillion, I had to look this up, 6 trillion transistors had been shipped and produced. Been produced. And it turns out 6 trillion is 10 to the 21. That's the first time I've heard that word. So basically, this is a real core, as I'm sure you guys know, it's basically a core part of us being able to talk remotely, us using cell phones, us using computers, us driving our cars, when the light's on, you name it, satellite communication, everything. And this is the latest chip. One of my new favorite companies is NVIDIA. So I'm hoping some of you guys recognize, some of your gamers recognize that name. But the 2020 NVIDIA, their latest chip, which is called the GA100 Ampere, has, this took my breath away, one chip has 54 billion transistors with a B.
Was that the 3080 or the 3090?
I don't know. This is just the numbers I picked up from the web, so I don't know.
That's incredible.
Yeah, it is crazy. It is insane. 54 billion.
That's pretty,
Go ahead.
well, I said that's pretty crazy considering we still haven't even gone to quantum, computing yet. We're still in traditional,
Yeah. I mean, traditional is like a relative word because, this particular chip was designed in a 7 nanometer or, 7 times 10 to the minus 9 meter. That's the length of a transistor in this process. And I don't know at what distance, you start getting quantum like uncertainty of where the electrons are, but it's got to be pretty close to this. So anyway, it's just core. This is like, oh, by the way, and then it's basically said that it is transistors are the most manufactured thing on the planet. That's just, we manufacture more of those as you can imagine. So basically the things that transistors get us for the most part or we can get gain, and we can get switching with transistors. And we'll talk about both of those. So most of the stuff, most of these 54 billion transistors in this NVIDIA chip are doing switching. And, you know, if you want to learn more about switching, you know, you can go take, you know, Verilog, VHDL classes or VLSI class. I teach that. So you can learn more about that. In a class like this, we're going to talk more about sort of something like a gain function, which is, you know, one of the core things that it does, a transistor does. So let's use a cell phone as an example. Okay, let's say you're just going to use it as a cell phone, not as a, you know, some way to surf the web or something. So I'm just talking about simply like, you know, you're having a call. So, you know, let's say start with a microphone. And, you know, that might be pumping out, I don't know, like hundreds of microvolts, maybe millivolts at its output, straight out of the microphone. So first thing you usually do is you gain that up to get, you know, go over above the noise. Then I think we talked about this in the first lecture, but, you know, the microphone's output also, you know, the frequency output is in the kilohertz range. That's sort of the human voice frequency range. And if you wanted to make an antenna from something that low of a frequency, the size of the antenna would be gigantic. It'd be, you know, hundreds of meters, say. It's sort of like, you know, you try to make a quarter wave antenna, and I don't remember the wavelength of a kilohertz signal, but it's, you know, very, very big. Like it's just not gonna, you know, something that even would fit in your house. So what you want to do then is you want to basically modulate this microphone, gained up microphone signal with some kind of a, you know, 1 to 2 gigahertz signal. So that's the sort of the signal frequency. You're modulating the audio with that frequency so you can use a shorter antenna. It's like usually at 1 to 2 gigahertz, depends on, you know, the cell phone standards, et cetera, that you guys are using. Next step, this is of course like a very, very simplified signal path, very simplified, right? Next step is something called a power amplifier. And this is what drives the antenna. Because, you know, you could be pretty far from a cell phone tower. And so you want to be able to basically start with a really, really big signal coming out of your antenna, you know, to give yourself as much coverage as you possibly can. And this is like the reason why people talk about, you know, if you have this stuff, they're worried about cell phones, you know, holding it close to your brain or whatever, just because they're pumping out a lot of power. So this power amplifier is pumping out a lot of power. And then, you know, this goes to some base station or something. And then on the receiving side, then, you know, you have a, let's try that blank. Let's say you got the receiver. So now, you know, this is somebody's receiving your call. And the first thing you do, you have a low noise amplifier. Because again, the signal from the base station to you, you could be pretty far from it. So, you know, you could be in the microvolts when you receive this signal from the base station. You know, when you're close, you know, you got to be higher. It's a very high dynamic range type of thing, but it could be a very small signal. And then you need to demodulate that down. So now you do the reverse of what you did before to get it back to the kilohertz range. And then you need some kind of a gain amp to drive the low impedance of, you know, so your speaker or something. So it's just like a real, you know, cartoon of what this thing might look like. But if you look at the signal path, you need gain here. Here, the oscillator still needs gain to oscillate. Power amplify needs gain. Low noise amplifier needs gain. oscillator, multiplier, gain amplifier. Everything here just needs gain. So you use gain a lot, even, I don't know if you guys have studied feedback theory, but even when you don't need actual gain, amplification helps you get linear signals, and it helps you get a controlled signal. So amplification and gain are extremely important, and they're used a lot. And that's what we're going to talk about first, is how do we use a transistor for amplifying or getting a gain circuit. Okay, so the other stuff I wanted to tell you guys is, transistor, some of the stuff I'm kind of making up. So, I mean, not the stuff I've said previously, but transistor, I couldn't look this up, but I think it means transistor. I don't know. I don't know if that's really the case or not. But the upshot is, sort of conceptually what it does is, let's say this is a transistor. So a diode, is a two-terminal device, right? So you got the, I keep forgetting it. So I think if you got the cathode and the anode, right? So you have the cathode, the anode. Resistor is a two-terminal device. Capacitor is a two-terminal device. Transistor is a three-terminal device. Okay, and what does that mean? Well, the cool thing about that is you can use an input to one of the terminals. This could be, most of the time in this class anyway, we're talking about some kind of a voltage input, control input, or current control input. So these are controls. Okay, so you can use some kind of an input in one of the terminals and get a change in current in the other terminal. Okay, and so that could look like, a changing current source. It could look like a changing resistor, depending on the type of transistor you have and depending on how you're modulating. But that's, the key thing, and we'll see why that gets you gain and so on. But this is the key thing. So this is probably going to be the first three-terminal electronic thing you've seen, or component. And basically that's the key thing it does. You have this independent terminal that controls the current through this other terminal. Okay. What else do I want to say here? Okay, cool. So then let's first take a look. So that's, so I'm sort of laying down the work for what a transistor is, how we define it. But let's first look at how you could get gain. So how can you get gain in a circuit? Well, so one way to get a gain, and I think this is the primary way transistors get gain, is through using something called a voltage dependent current source. Okay, so you guys are familiar with current sources. So this current source is something that outputs a current with very, 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 basically infinitely high output resistance. Okay, so no matter what voltage if I look at this current source, no matter what I do here, so let's say this is this voltage Vx. Okay, I could do anything. I could take it to plus infinity, minus infinity voltage, because that this current source has infinite infinite output impedance. It just always is pumping out the same current. Doesn't matter what the voltage does. Okay. So that's just the definition of a current source. Okay, so basically that's a current source. And a voltage controlled current source has another terminal. So this is our 3-terminal device. Okay, so this is our, the common, say. And this is the input. Let's call it V1. And so what this thing does is it has I is some kind of a function of V1. So I'm actually, let me write it a different way. You have the current is a function of V1. Okay, so basically, if you change V1 here, if you change V1, the output current's going to change. But you could change this node, this output node here, put different voltages here. I mean, this is an ideal situation, and you won't, the current won't change, okay, respect to the common. Okay, so let's see how we can use this for gain. So this is called a voltage dependent current source. Oops, I moved stuff around here, sorry guys. Okay, so that's what that's called. So it's a current source that's dependent on the input voltage. Okay, so if we have such a thing, and I'll show you guys how you can hook up a bipolar transistor to create this kind of thing. But if you have such a thing, you can get a gain out of it by, so I'm just gonna draw some stuff around it. So let's say I have this current, and then let's say the current is some k times function of V1. Okay, and V1 is our input. Okay, and then I'm going to put in a voltage source at the input. And then I'm going to hook up a resistor on the output. Sorry, this should be R sub L. So the stuff in black is our voltage controlled current source, and the stuff in red is stuff external to that we put in there to create a gain element. So let's look at what these things mean. If you just look at this circuit, V out is minus K or L V1. So basically you've got this current. The minus is because the current's going this way in, and that current is creating the voltage V out when it goes across R sub L. So the equation for V out becomes minus K R L V out. And I'm going to define this concept called gain. Okay, and this is defined as V out over V in. So this is like how much is V out amplified over V in. Okay, so then, by the way, in most gain elements, or most amplifiers, I should say, most amplifiers are inverting amplifiers. Most amps are inverting. And we need to keep track of that minus sign, but basically people just kind of ignore it, except knowing that the polarity of the output is going to be inverted with respect to the input. But when you talk about gain, you don't talk about negative gain. You just call it an inverting amplifier, and you really look at this KRL as the gain in this particular case. Okay, so if, so I'm going to rewrite this. So if I have a gain, and then V1, by the way, notice V1 is just Vn because we've just applied this Vn voltage into the V1 directly. So the gain becomes V out is minus K RL V in. So that is V out. And V in is just V in. And then you cross the V-ins out, and the gain of the circuit, it becomes minus K R sub L, which is, again, the ratio of the output to the input. And so if K times RL is bigger than 1, we say we have gain in the circuit. If it's less than 1, you have attenuation. Okay, but most of the time right now, we like gain to start with. What I want to say about this. No, that's pretty much it. So it's pretty clear. I think we're going to see this over and over again. There's a lot of different ways to get gain, but most of the transistors we'll see in the circuit are current sources into resistors, okay? Because that's how these transistors like to operate. You could do current, basically transistors driving other transistors as loads also, but basically the basic element, not to confuse you guys, but the basic element is a current source driving some kind of a high impedance load, which is either another current source or a resistor or something like that. But just don't think about this for now. Just want to. Okay, any questions about that so far? Let me just draw one more thing for you guys. So if I was gonna basically look at what this would do. If let's say this is T time, this is voltage, and let's say this is an input. Oops. It's basically a sine wave with some kind of a peak voltage. Okay. If KRL, oops, is greater than 1, let's say it's, I don't know, 4 or something, 5. What the output would look like is something like this. So this is V in, this is V out. Would look like, so remember it's inverting and it's amplifying. So it would do this. So where you got peaks, it shouldn't be, sorry guys, it's not distorting the sine wave. I'm just doing a bad job of drawing a sine wave. But it does something like this. And this thing is KRL times VP. Okay, and then again, notice it's inverting and multiplying the input by KRL. Okay, any questions about that?
Just why did you get rid of the negative, Professor, if it's opposite?
Well, so in yeah, go ahead.
No, I was just asking about the minus sign. Why?
Yeah,
because
I conceptually kept it because I inverted See, this is inverting the signal, so that's the minus.
Yeah, exactly. That's what I can see from the graph that is inverted. So that's why I'm confused why you don't express it as negative. It should flip, right?
What's that?
Like the negative sign should flip the VP
Yeah,
by multiplying by
the
negative
actual,
one. Like,
the actual gain is minus KRL.
mhm.
So the actual gain.
Oh, I see.
So it's inverting. So I'm drawing the actual gain, but when you talk about gain, you don't. So sorry to make this confusing, but when you talk about gain, you don't call it, negative gain of 4. You just call it a gain of 4 and then inverting
So
it.
you're just expressing kind of like the magnitude, right?
Yeah,
Just,
you're exactly. Yeah. So
thank you.
in
Yeah,
your
I see it now.
equations, in your math, in your graphs, you still express the minus sign. Like in this graph, I basically drew it inverted because of the minus sign. But the peak is still KVRL, but it's inverted. It's an inverting amplifier. But I don't call the gain minus KRL. I call the gain KRL. Does that make sense? It just convention.
Got it. Yeah, like we can't have any gain if it's negative, correct? Just by assumption.
If it could. So what a negative gain really does is means that you have amplified the signal and you've inverted it. That's kind of what a negative gain looks like. And in fact, that's how most amplifiers work, most gain elements. You amplify the signal and you invert it, just because that's what electronics like to do. But just verbally, people typically don't say like negative gain. They just say gain. So it's more of an expression. But when you do the problems and when you do the math and do the drawings, you can just keep track of this minus sign, as you need to keep track of it. Does that make sense? I know it's confusing, but it's just not calling it negative gain or a negative gain of 10 or minus 10 as the gain is kind of is just a convention. But you still use the negative sign, all your math, etc. I hope that didn't confuse you too much. Does that make sense, man?
Yeah, I think when we see an example, it'll all make sense.
Okay, sounds great. Okay, cool. So let's see, what else did I want to say? So a bipolar transistor, and now you're gonna have to trust me for a second. So a bipolar, the reason I went through this discussion of a voltage dependent current source or voltage controlled current source and how we can get a gain out of it, etc., is because you can model the bipolar transistor in a certain operating mode as a voltage controlled current source. Okay, so if you have a bipolar transistor, and I'll show you guys how in a second here, you can model it as so here's V1 plus minus. So the only thing is this current source, this I out, is actually, it's an exponential relationship with Vn. Okay, which means you have a very strong but nonlinear voltage controlled current source. Okay, and these are the terminals. So we said a transistor is a 3-terminal device, and so is a voltage controlled current source. So this is the terminal 1, terminal 2, which is the common terminal, and this is terminal 3 that, at least initially, we're going to use as the output. Okay, so that's the upshot. The upshot is that a voltage-controlled current source, we can use it to get gain or amplification, and we can basically operate a bipolar transistor to make it look like a voltage-controlled current source with an exponential dependence of the current on the input. Which actually makes it a pretty, like a very sensitive device. Because, you know, when you have this exponential relationship, just if you're in the correct bias region, a small change in V1 is going to give you a big change in current, which means that you could potentially get a lot of amplification out of it. Okay, so I'm going to sort of segue back again. So now let's look at what a bipolar transistor looks like. Okay, so when you remember a diode, basically if I draw a diode, this is the cathode, this is the anode. And if I draw it as a chunk of silicon, it looks like a p-type device or p-type material next to an n-type material is a p-n junction. And so we need to contact those, and you end up with the anode and the cathode. So that's what a diode look like. A bipolar transistor looks like you basically take that thing, that N and P, and then stuck another N here. So you're sandwiching, you know, a P section between two N sections. Or you're sandwiching a, well, let's talk about this first. So basically you have, and basically what you do is you end up with 3 terminals, okay? Or you need to have 3 connections to these because you have 3 regions, right? You have this N, you need to make a contact to this N on top. You need to make a contact to this P in the middle, and you need to make a contact to this N. So now this is where we get this 3-terminal device. And just like we have weird names for diode terminals, we have also weird names for the transistor terminals. So they call this the collector. They call this the base. And they call this the emitter. Okay, and then the circuit, so just like the diode had a circuit drawing that looked like this, this has a circuit drawing, bipolar transistor that looks like this. So this terminal is the base, this terminal is the emitter, and this terminal is the collector. Again, like a 3-terminal device. And then these are just definitions, okay, but they'll come up over and over again, okay? So this voltage we call VBE, stands for voltage between base and emitter, which is called VBE. Start calling it VBE. There is the voltage between collector and base, VCB, okay? And the voltage between collector and emitter, so that's VCE. So voltage between collector and emitter, base and emitter, collector and base. Okay, so those are different voltages. Then we'll talk about what they'll actually do. All right, so that's a bipolar transistor, but you could have really the way you get a bipolar transistor is when you have two regions of the same polarity. So these two are the same polarity. They're both N-type, and they're sandwiching a region that's the opposite polarity, which is a P-type. So you could also, so this is called the NPN bipolar transistor for NPN, whoops, NPN bipolar transistor. You could also have a PNP bipolar transistor, which is two P sections sandwiching an N section. And again, so this is called the PNP, and again, this is called the base. This is called the collector, and this is called the emitter. So conceptually, this works like the NPN. The PNP works like the NPN, except everything is reversed, where you have currents coming out in the NPN, you have currents going in on the PNP, and et cetera. Just all the polarity of all the currents and voltage, et cetera, is changed. So the schematic for the PNP is this: base, collector, and emitter. Okay, so the difference is that this arrow is always on the emitter side. In the NPN case, the arrow is pointing out. In the PNP case, the arrow is pointing in. So out versus in. So this is a PNP transistor, and this is an NPN transistor. Most of this class, I don't know how long we're going to spend on bipolar transistor, probably like another 4 weeks or something, if not more. But most of the class we're going to spend on PNP. Okay, and just at the very end of the bipolar section, we're going to look at PNP and see the differences between PNP and NPN, and see how that affects the performance of the circuits will do. The reason for that is conceptually, again, PNP is exactly like NPN, except everything's inverted. So if we look at the NPN and come up with the circuits, it's pretty same topology as you can use for PNP, except you have to invert everything. But we'll see that. So most of the time we'll talk about NPNs. So back to
Professor. Quick question.
Sure.
The voltage in between two terminals holds the same signs for both? Like the ones that you draw for the NPN are still the same signs for the voltage in between the terminals, or is it different?
It'll be different. I mean, the polarity of the voltages, it's called the same thing, but it'll be different. So like, for example, like but it's called the same thing, but it'll have the opposite polarity to work properly. So you'll still have VBE for a PNP, but you'll see in a minute that VBE for an NPN, you want to keep that positive. Whereas for the PNP, in a few weeks, you'll see that you want to keep the base emitter voltage negative, meaning that you want the base at a lower voltage than the emitter for a PNP.
Oh, okay.
And for an NPN, you want the base at a higher voltage. It's still called VBE, except it's just the polarity is reversed.
Is that to avoid breakdown?
I'm sorry?
Is that to avoid breakdown?
No, it's to put the device in the appropriate bias condition.
To make it work, right? To turn it on.
Yeah.
In a sense.
Yeah, and we're probably, yeah, we're just like a little bit far away from that. So bear with me for another couple of minutes, and then we'll talk about how you want to hook up the voltage.
Okay, thank you, Professor. Just good question. Thanks.
Sure.
Professor, I do have a question if you don't mind.
Sure.
So I know that they're probably just, arbitrarily given, but could you elaborate a little bit on why the names are given, like collector, base, and emitter?
Uh,
It doesn't have to be super in depth, just maybe like an idea.
I just been making stuff up. I don't know. I don't know. So, okay, so I'm going to make something up, but I think this is the answer. As you'll see in a minute, so the way this stuff works is the emitter is emitting electrons. So also, God, my problem is I'm also, what do you call it, amateur historian. So I love the history of this stuff, but it's just kind of confused the heck out of you guys. And some of it is conjecture on my part and other people's parts. So the transistor really replaced the vacuum tube. The vacuum tube, which is, you'd only hear about if you're into like high-end audio or something these days, was, tube that maybe was the shape of the size of a cigar or something. And it was a three-terminal device, except it was an electron beam in a vacuum chamber and so on. So you actually had a terminal was actually emitting the electrons, and another terminal was collecting the electrons. And the base, I don't know why they call the base. But as you'll see in a minute, the way this device works is that the emitter is sort of emitting electrons into the base, controlled by the voltage between base and the emitter. So the emitter is emitting electrons into the base, and then the collector is collecting those electrons. So that's kind of how I thought about it. Is that really why they're called emitter collector? I think so, it makes sense, but don't know for sure.
Thank you, that helped a lot. Thank you.
Sure. Okay, so let's see. So one other thing. So here we have, so I'm going to go back to this NPN most of the time. I'll talk about this NPN. Okay, so NPN. Okay. So it's tempting to get kind of too clever and think about this as two back-to-back diodes. So, you could incorrectly think that, hey, this just looks like this. I have two back-to-back diodes. These are just electrically connected. And, I'm going to I'm connecting my base. And this is a collector, this is my emitter, or, like something like this. This is what this thing looks like, right? You could just say, hey, this is a base. So it's tempting to think that this is what you got, but this is not correct, okay? The reason is the whole way that this transistor device works is this base region has to be physically narrow enough I mean, I'm talking about like physically narrow, like how many, whatever, how many fraction of a micron thick it is, that basically the emitter and the collector can interact with each other through the base. Okay, so this gain, this transistor action, you really won't get if you just hook up two diodes like this or two NPN junctions back to back like this. You have to basically create a very, very two N-type regions with a very, very thin base. Very thin base region.
And that's so that the electric field doesn't hinder it, correct?
Yes and no. We'll get to it right now. Let's do it. So it is true that there's like the electric field, you know, you don't want the electric field to hinder it. So let's look at it. So what I want to say. So, okay, so let's first talk about the voltages, and then we'll talk about the electric fields and how things are moving around. So for most of the time, we'll hook up a bipolar transistor in something called forward active region. You can hook it up in different ways, but this is how you're going to get gain out of a bipolar transistor. And this forward active region is just by definition this. Okay, you want to have a base emitter voltage. So I'm going to put a battery here. And so this is, I'm going to ground this and ground this, but they're really, you know, connected together. So I want to make this V base emitter around 800 millivolts. So basically what I'm doing is I'm making this forward bias. I'm making the PN junction between the base and the emitter forward bias. Okay. And then I'm going to put another battery here between the, remember that the way this device worked, at least in this way, the common node was the emitter. So I'm referring both the base and the collector things to the emitter, which is grounded in this particular case. Okay, so I'm going to make this collector emitter voltage 1 volt around. That could be higher or lower. No, I'm sorry, it could be higher. You probably don't want to make it much lower. And so what that does, if you notice, so if the base emitter voltage is 800 millivolts and the emitter is grounded, this makes this node 800 millivolts. The base 800 millivolts. The collector is 1 volt. So the collector base voltage ends up being 200 millivolts. Okay. And it's the N is 200 millivolts above the P, meaning that this guy is reverse biased. So the base emitter junction is forward biased. The base collector junction is reverse biased. Okay. So let's see, what is this going to look like? So I might just, maybe should stop. So I'm just going to say this last thing and kind of stop it here because this is a good stopping point. So going to what we were talking about emitting and so if you, sorry, the electric fields and emitters and collectors, etc. So let's say this is an NPN. So this is the emitter. This is the base. And this is the collector. Okay. Now you're gonna have to like remember back in the PN junction discussions. So if this PN junction between base and emitter, if that PN junction is forward biased, nothing stops. So this area is an N area, meaning the majority carriers are electrons. So there's a ton of electrons here and very few electrons in the P side. Just the definition of N and P. So P has a lot of holes and very few electrons. On this side, we have a lot of electrons, very few holes. So if this is forward biased, the electrons are going to want to go where the electrons want to move from where there are a lot of electrons here in the emitter to where there are few electrons. So that's in the base, right? Remember the diffusion, we're basically going to get this diffusion current between the emitter and the base with electrons going in that direction. Just because this junction between, let me just write it down. So this junction here is forward biased. Forward biased. So nothing stops diffusion currents. Okay, and then by the same nature, you're going to end up having a bunch of holes going from the P side where they're abundant to the N side where they're few in number. Okay, and to get the most out of this device, as you'll see why in a little bit, you want this current of electrons to be a lot higher than this current of holes. And so the way you do that is by making this part like very highly doped, very high concentration N type compared to the P. So we call that N plus. It's a much higher doping concentration than the P doping concentration. Okay, that basically assures that the electron diffusion current is going to be a lot higher than the P diffusion current when you're in forward bias. Okay, so then we said the collector base junction is reverse bias. Means that there is a depletion region here, okay, where we're depleted of carriers, but where there is an electric field. Okay, so we've got a reverse bias. We had a built-in potential that gave us the electric field, again, remembering back to the PN junction days. And so we have an electric field built there. So that prevents diffusion current from the N into the base, from the collector to the base. There's no or very little diffusion current there, or from the base to the collector. But remember that this depletion region has a physical width. This has a physical width, and the higher this this voltage, this reverse bias voltage, the wider that is. Okay, so if this base region, the width of this base region is very, very short, what happens is these electrons that get dumped, so diffusion current from the emitter into the base, and then what happens if base is very short, most of these electrons end up in the depletion region and then get swept or get collected by the collector. Okay, so these electrons basically go from the emitter to the collector. And they basically show up as like a current that has a reverse polarity. So it looks like you have an electron current going the other way, basically, right? And then, so what happens is by changing the base emitter voltage, we are increasing or decreasing this diffusion current from the emitter to the base, and therefore the current from the emitter to the collector. So we have this one terminal that's controlling the current at this other terminal. Okay, with this guy being the common voltage. Because this PN junction here is forward bias, so we get current diffusion current going from the emitter to the base, and then if the base is narrow enough, it gets captured, gets collected by the collector, and then appears like this electron current. And basically the base emitter voltage is controlling that current. Okay, so that gives us our voltage controlled. Let's write it properly. Sorry, guys. So we want a voltage controlled current source. Okay, so the controlling voltage is the base emitter voltage. Okay, and if the collector base junction is reverse biased, then the current source is from the emitter to the collector. Okay, so we end up with our voltage controlled current source. And then the other thing to remember is that, again, if you guys remember the PN junction, this current as a function of the base emitter voltage, so I emitter is I sub S as a function of the base emitter voltage over VT. So it's an exponential relationship of this current compared to the base emitter voltage input. So it's a very, very high sensitivity type of modulation. Okay, and the reason you want this whole current to be much smaller than the electron current is because, you know, this current has to come from somewhere in steady state. It's coming from the base. Okay, so this base has to source these holes, and you want to have a good transistor. You don't want this to be pulling, like something else is going to be driving this. You don't want to have to make this guy source a huge amount of current to get a huge amount of current coming out of this. You want to have a very light load on whatever is driving you, so you have a best device. So that's why you want to have this asymmetry in the electron to the hole current. Okay, guys, I think I'm going to stop there because, you know, then we're going to go down this other path, and you know, it'll be like a half an hour discussion. So I thought I'd stop early here. Again, giving you guys a flavor of the bipolar transistor and how it works. And so we'll stop early tonight, and then we'll pick it back up after your quiz on Tuesday. Any questions? I hope I answered some of your earlier questions, but anyway, tell me if I answered your questions or any new questions.
I just want to make sure, Professor, I sub E is the current of the emitter? I mean the emitter?
Yeah, that's the current of the emitter. I'm sorry. And,
okay.
and then I collector is where you're really interested in, because that's this guy, is approximately the same. And we'll talk about the difference between those two. But it's approximately, if you collect, if this base is short enough, and if you collect most of the emitter current, then the collector current is almost the same as the emitter current. It's a little bit less, but it's almost the same.
Okay, thank you.
Sure. Any other question, guys? Okay, so I'm going to stop it here, and then if you guys have any questions on the quiz, I'm not really doing anything this weekend, so just shoot me some email or whatever. We can set up a call or whatever if you guys need some help on the homework or getting ready.
That sounds great then. Thank you.
Thank you, Professor.
Thank
Are you
you.
gonna have office hours on Monday, Professor?
Yeah, I'll have office hours on Monday and tomorrow, Friday.
Okay.
Professor.
Yeah.
I remember we briefly discussed about the homework, but I see it now. But it's just that the formula you have for 3.10
Yeah.
circuit B, it said V out equals V in minus 2, but there's a voltage drop by VD on.
Right.
On the homework solutions.
Yep. I screwed that up. So we were
Okay.
talking about that right before class. So thanks for pointing that out. But yeah, I got that wrong. So I'll fix it up.
Okay. Thank you.
Thanks.
Thank you, Professor. Have a good one. Thank you.
Have a good one, Professor.
Yeah.
Bye.
Thanks.
Thank you, Professor.
Bye. God bless. Bye-bye.
Bye.